Swayam Prabha. Digital India. Educated India.
And so let me start this year being International Year of Quantum Science and Technology. So exactly 100 years ago that quantum mechanics came into being as a theory with its own conceptual basis. All right, that's very important, as its own conceptual basis. And what I wish to focus on is what happened here in 1925. And what happened in 1925 was very special, and that's what made this theory one with its own conceptual framework, was that Heisenberg jettisoned everything, classical ideas that people had about quantum mechanics, and proposed that a new theory be built only on the basis of what we can observe. Right? And that's very important. And the moment he said that, that means our way of thinking about nature also changed. So it was really an epoch-making thing, and of course it started an era. So whatever he did, and I hope to convey that to you, it was highly imaginative, very creative, out of the box as they call it today, and it really put, because of the way he was thinking, humanity on a new way of thinking about things. Whatever he did, however, began in (1900). 14th December 1900 is called the birthday of quantum mechanics, because that is the day Planck gave his talk on the idea of quantum in a German Physical Society meeting. All right, and here is the person who did that. If you want to know more about him, there is a fantastic book about him which came about 2 years ago. He was a person who was really a father figure for a lot of physicists and science in general in Germany. Despite all the setbacks, he did a lot for German science. The youngest son later was executed by Hitler. So he lost his elder son in the First World War. 2 of his daughters died during childbirth. So, but he kept going. What he did was he proposed that black body radiation, which was a big problem at that time, and I think I'll keep going back and forth between technology and science, could be explained only if you assumed that the harmonic oscillator that gave out radiation, its energies were quantized, right? And therefore, the energy level difference was given by HNu. It was not going to zero. It could not vary continuously. And the average energy of an oscillator was this. Why I said science and technology? I mean, if you think about it, who would be making a box, heating it up, let the radiation come out, and analyze it? I mean, the person had to be crazy. But the idea was, it was driven by the need to make very good incandescent bulbs. One wanted to understand how the temperature of those filaments changes the spectrum of the bulbs. So technology and science go hand in hand, and we have to learn to appreciate each other. So here was the average energy, and therefore he had worked out something. This is a beautiful calculation through which he got this, and let me just comment on that. This formula is for the energy density of radiation inside a black body at frequency nu. This is spectral, so it's between nu and nu plus d nu. And this he worked out through equilibrium between the radiation and the oscillator. And all this was a classical calculation, and through which he got this spectral density. How good was this answer? And this by the way, was a universal curve, and this was applicable everywhere, no matter where you went. So this is the latest data I'm showing you. This is taken by this cosmic microwave background spectrum from Kobe. This is a satellite by NASA which was sent up. And this is the spectrum, experimental spectrum at roughly 3K. And theory sits right on top of it. And the accuracy the experimental accuracy is so good that the error bars are within the thickness of the curve. So this is how beautiful the theory is. So it has withstood the test of time. So takeaways from this work were that energies of harmonic oscillators is quantized. A new constant H is introduced, which is related to quantization. And I also wish to point out that it is through these investigations that Planck also calculated the value of Boltzmann's constant. And once he got the Boltzmann's constant, the Avogadro's number, and once he got the Avogadro's number, the electronic charge, because you divide the Faraday constant through this thing, for the first time. Before that, Avogadro's number existed only in concept. So this is the first time that he did this calculation. Later, of course, Millikan's experiment, confirmed that that was the electronic charge. Right? So this was the beauty of this whole thing. And by the way, most of us are into teaching business. It's fun to teach quantum mechanics, to tell them that explain every phenomenon, get a formula, not by looking into nitty-gritty, just use H if you think something is quantum mechanical, and use dimensional analysis. Most of the time you end up getting the right answer. So even, for block oscillation period, I've used that and it comes out all right. So slowly the idea of quantization grew from 1905 onwards, right? And some of the people who contributed to it are these: Sommerfeld, Nernst, this is Lawrence, this is Stark, Zeeman, Pauli, Max Born, some of those people who contributed big time into this development, and others I'll be talking about through this talk. So first question that arose in this was, shouldn't radiation be quantized too? Right? What gave rise to this question is this sort of inconsistency, which I'm going to point out, is that Planck's relationship, this relationship I talked about, was derived using classical formulas for everything. It used classical formula for the energy of oscillator. It used classical ideas about the energy of radiation. It used classical formula for the exchange of energy between the oscillator and the radiation. But finally, this answer was obtained. So this is classical. This answer was obtained by using the quantum idea for average energy. There is some sort of an inconsistency between what was being done. And if you want to just make an analogy, here's the analogy. Imagine a bank dealing only with 200 rupees notes. But you say that I can exchange money with it using coins. That's an inconsistency, using very small unit, but it deals only with 200 rupees notes. So that is the kind of consistency one is talking about. And this was resolved by this man, right, who at one time lived here. Right, that's a cartoon about Albert Einstein. So what he asked, and this is a beautiful paper that the translation available in American Journal of Physics, and this is a para which I have kind of written in my own words, but this para is one of the most beautiful paras written. I usually make my students read it in communications class. So he says, despite complete experimental verification of wave theory, it is conceivable that such a theory with continuous energy flow will lead to conflicts with experiments involving light generation and conversion. So this is fine, but the moment you talk about light conversion and generation, there will be a problem. And he argues through entropy arguments how you can treat light as collection of particles. And the thing that he explains through this is photoelectric effect, which we all know, and I just want to remind you, it's ejection of electrons from a metal surface when you shine light on it, and the ejection is without any delay, it's immediate, requires a minimum frequency, and no matter how large intensity you take, you require that minimum frequency. So he explained it using this concept of particles, light-having particles, and I just want to show you schematically or through this cartoon the difference. When you think of a box of marbles, classical picture was that there is a wave coming, and so it will be like you're blowing air on it, or you have some sort of a water stream coming into it, and the marbles cannot be knocked out. Whereas you hit it with a particle, it comes out. That's the difference between the classical picture and quantum picture. So here's the photon coming in, and it knocks an electron out. And that's how he could explain photoelectric effect. Along with it, he also explained two more things. One which I'll talk about is the Stokes shift. That is, light which gets scattered from a molecule, rather than Rayleigh scattering, its wavelength becomes longer. And that is also explained because the photon comes in, gives part of its energy to the molecule, and then it gets scattered with smaller frequency. So that's what Einstein did in his paper. You see how profound this was, and now I'm going to take name of an Indian. I want you to look at this picture of a comet. Whenever you look at the comets, comets have these two tails. One is a dust tail, another is the iron tail. And people did not understand how this was coming about, right? So the person who did this was an Indian named Meghnad Saha, right, who's also known among other scientists as the father of modern astrophysics. He was nominated for the Nobel Prize for 7 times, including 2 by Arthur Compton, who nominated him twice. So he is known father of modern astrophysics because of this formula, where he applied quantum mechanics, which was just coming up, to understand the existence, the abundance of ions and atoms in a stellar, in a star or something, right? And through this, the modern astrophysics came about. But this is not something I'm going to talk about. I'm talking about something else. And that is this, Saha's consideration of the tail of comets. What he said was, and if you see this paper, it's beautifully written. He considers the pressure of sun's light on this comet and says the pressure is not enough if you take Maxwell's equation. Rather, if you apply quantum theory of light, when a light pulse of energy h nu is absorbed by a molecule of mass m, it will be thrust forward with an impulse of momentum h nu by c. And the explanation offered closely resembles Einstein's explanation of velocity of photoelectrons. So that was his contribution towards understanding this. However, now we know that this explanation is not fully correct, because now we also think of the solar winds that carry these ions. But his idea that quantum mechanics should be applied to understand things, and there has to be a particle hitting the comet so that there is an ion tail coming out, was right. And with this was born the idea of applying quantum mechanics to stellar objects. So that was his contribution. Another Indian contribution, nominated 11 times for the Nobel Prize, was S.N. Bose, who treated black body radiation as a collection of particles. Because before that, there was a lot of talk about, yes, Einstein gave this, photoelectric effect can be explained. However, are they really particles? And if they are particles, what kind of behavior do they have? So what he said is, treat them as particles of having this momentum h nu by c, and consider the corresponding phase space. Distribute these particles not by counting the particles, by counting the cells of volume h cube in this phase space. Forget about counting the particles, right? So he ignored the particles part, and that has profound interpretation, right? And he distributed them among these cells and optimized them, the number distribution, to maximize the entropy, and then got the correct formula for the Planck's radiation. So takeaways from his work are, number of particles is not conserved because you could put any number you liked. Also, since the number of cells and not the particles are counted, the particles are indistinguishable. You don't really care which one is going where. It's just the number that's going there. Also, particles are not treating as statistically independent. You could put any number anywhere. You're not, again, doing each particle counting independently. And what follows is the quantum statistics, which was a new statistics followed by these particles, right? And this here I'm being specific about photons. Of course, everybody knows that Einstein later generalized it to particles where the number is conserved. And here's a man who did it. Of course, he is known as the creator of quantum statistics, father of concept, boson or God particle, right? And next question we answer is the quantization a general rule of nature, or is it limited to electromagnetic interaction only? Because so far we have talked only about electromagnetic interaction. And the answer again was provided by Einstein, who said that the result, the average energy h nu by E h nu by kBt minus 1, the average energy is follows the same formula as the photons, should be applied to mechanical oscillators also. And therefore, where it comes from, that mechanical oscillators are also quantized, have quantized nature. If they have quantized nature, then this follows. And therefore, with each degree of freedom having this energy, n atoms will have 3n degrees of freedom, and this will be the energy. You may say, so what is the big deal if you do this, right? The big deal is, and that time it was not very clear, that with this, the implication for specific heat of solids is that it goes to zero, temperature goes to zero. Another time where technology played a big role. Remember, we are talking about 1905, 1906, 1907. At that time, low temperatures were not available. So everybody thought, because the experiments were at higher temperature, that formula that Cv is 3R is okay, Dulong-Pettit law. And here's a man who's saying that apply to mechanical oscillators and the specific heat goes to zero, right? And right around that time, the machines that could create low temperatures, they could liquefy oxygen and air, were developed, and people started doing experiments into lower temperature. The person who was really into it was this man, Walter Nernst. I've shown his picture earlier. He had come up with this idea that entropy of systems vanishes as T goes to zero. We all teach it in thermodynamics, right? And implication of that is that specific heat goes to zero as T goes to zero. By 1910, you had good machines, good technology, so that one could go to low temperatures, and they confirmed that as Cv goes to zero, T goes to zero. This is the science and technology part of it. The human aspect is that with this, Nernst got really enthused about quantum mechanics. Before that, he did not believe in it. He started saying, oh, it's really a genuine theory. Let's work on it. More than that, he started organizing these Solvay conferences. He went to Mr. Solvay, who was a Belgian, and said, let's give some money. There's this new theory which is coming about. So he absolutely, started believing in it, and he played a lot of good role in popularizing it and letting people understand this. And for completeness, I want to show you this beautiful graph by C.V. Raman. This is the specific heat of diamond, and as temperature goes to zero, you see it going to zero beautifully, just like that exponential law, right? So this is the part where one is talking about quantization of energy and its consequences, but now further development takes place. And the further development is that people started thinking about, can we apply quantum ideas to atoms, right? This is also, you have to understand, this we are talking about 1910. This is a conceptual jump, thinking that I could somehow relate this constant called H, which somebody has said about, harmonic oscillator, somebody has said light is coming in terms of H nu, that it has something to do with atoms. Really, it's a great thinking. And the person who did this initially was this man called Arthur Haas. He preceded Bohr by 3 years. And what he did was that I'll relate Planck's constant with atomic spectrum. He was actually trying to look at atomic sizes, but he ended up also connecting with atomic spectrum. And this is what he did. He said, hydrogen atom is made up of positive charges of radius A, and electrons move on that surface, and therefore they satisfy this classical law. Important thing, however, was that the potential energy has to be h nu, where nu is the frequency of turning around. And he did some more calculations, related nu to nu infinity of Balmer's formula, and he got Rydberg's constant, which was just a factor of 2 away. We may say today, what kind of calculation is this? A factor of 2 away? But think of this. He got it in the right direction, right ballpark figure. And the conceptual advance he made, that you connect H with atomic properties. Bohr did not know about it, but that's okay. But we have to give due credit where it's due. The next person, of course, everybody knows, since our days on 11th, 12th grade, that Bohr model of hydrogen atom spectrum, where he gave the nth energy is minus 13.6 z square by n square. More important, he gave, this should be the frequency. The beauty of hydrogen, the work of Bohr is he combined two concepts. those of us who are involved in making these question papers for competitive examination and all that. Oh, two concepts meaning, moderate, hard paper question. One concept means easy. So he did a hard problem. He combined two concepts of getting the quantized energy levels and saying that when the energy is emitted, it's in terms of photons. So he combined these two concepts and got this answer. And of course, he became very famous. I particularly want you to pay attention to this cartoon of his, where he's being honored, and you see the number of malas, more than a bridegroom in India. So there he is. Much more important than his becoming famous through this and becoming a celebrity was that he was given a really generous grant by Danish government to establish an institute. And it was not just Danish government, it was also a company called Heineken. So they were willing to pay for, whatever. So, and here is the institute. This is the Niels Bohr Institute, and Niels Bohr with Einstein, this Compton, I think, and this is Rabbi. This is, I've deliberately put it here, this is a fantastic play called Copenhagen, which is about interaction of Heisenberg and Bohr. Just when the Second World War was starting, they met without anybody there, except maybe Mrs. Bohr was there, and what transpired there, nobody knows. This is a guess about this. It's a lovely play. And I also got it done at IIT Kanpur in one of my courses by the Dramatics Club. And about 1,000 people from all over campus attended it, and nobody moved. So this is a fantastic play. But nonetheless, what is important is that when this institute came into existence, a lot of young people from around the world started coming there. And just they would discuss quantum mechanics with fierce exchange of ideas. They thrashed out ideas, and therefore the quantum mechanics started taking shape. They would work out different things, and Heisenberg was one of them. Right? One of the things that came about during that time, Bohr model is only about hydrogen atom, but how to apply it to other systems was this general quantum condition, which is that action, and this is something called the Maupertuis reaction, P dot dl around, for periodic system, you calculate this for one period and it is quantized. It's n times the Planck's constant. So this was a new condition. Beauty of this condition is that it has Bohr's condition in it, right? You apply it to circular orbit, this comes, but now it became more general. I just take one example, 1D harmonic oscillator, it gives the right energy. And Sommerfeld also started applying it into, elliptical orbits and things like those, and got all sorts of things, new quantum numbers and everything. So, new quantum condition, this became the condition for doing quantum calculations for the near future, right? And through all this, the question came that we are calculating frequencies beautifully. They matched. Hydrogen frequency is perfect. Can we determine the intensity of light? And the answer is, let's explore that. Classically, the radiation arises from acceleration of charges. This Maxwell's theory gave. And total power radiated by charge performing simple harmonic motion is given by this formula, also known as Larmor's formula. This was well known. Can we apply this to quantum system? Right? So let's explore that. Can we apply this formula, Larmor's formula, to quantum system? And the answer is no, it cannot be applied. And that's where the quantum mechanics started differing from that. You see, in Bohr model, electrons do circulate around with periodic frequency omega n, but the radiation mechanism is absolutely different. The radiation is by jumping from one orbit to the other, whereas in Maxwell's theory is through acceleration. Two are absolutely different, so one doesn't know what to do. One doesn't know how to calculate frequencies. I just wanted to go back a bit to this formula which I showed earlier. Here, the intensity is proportional to the amplitude square and proportional to the frequency raised to 4. And if you recall your 12th grade physics chemistry, this is what gives rise to the blue sky, right? Omega raised to 4. So remember this omega raised to 4 thing, and that I cannot apply this formula to classical to quantum systems shows here also. This is peaks of hydrogen atom spectrum, and you see this way the frequency is increasing and they appear to be random. Intensity appears to be random, not omega raised to 4. So experimentally also it's clear it cannot be applied. So classical formula fails because the mechanism is different. What do we do next? Next contribution again comes from Einstein, who says, look, you cannot think of this mechanism. He did not give the mechanism, but what he said was that the process of radiation in an atomic system is very different. It's probabilistic. If there is an atom in the higher excited state, there is a probability that it will emit a photon and come down to lower state with a probability A. At the same time, it can also come down because of the radiation presence. That was a new thing, a stimulated emission of radiation, which is responsible for laser action. And of course, it absorbs when you in the lower state and goes up. So he gave this new idea that in quantum mechanics, radiation has to be calculated probabilistically, and that amplitude probably is related to that amplitude, but that is, we are not there yet. So this was Einstein's idea. It of course gave rise to lasers later, but this was an important contribution of introducing that think of this mechanism as different. Quantum jumps are probabilistic. Just if we accept this idea, just a calculation, approximate calculation of A would be classically, h nu by 2 pi, that's the energy of a photon. It comes out with probability A, and this should be equal to the radiation coming out if I mix the two quantum and classical ideas, right? And it gives A equals this. This is a quantum mechanical quantity, but I am calculating it through classical ideas. And as an example, I calculate this for a charge oscillating with frequency omega, and here's the answer, right? Is this calculation okay? The answer is no, because this calculation is really a hodgepodge of classical and quantum concepts. X naught is, the amplitude is calculated using a classical formula with a quantum mechanical energy. Then I'm using quantum mechanical formula for the radiation, the classical formula for the radiation. This is not satisfactory. What would a quantum mechanical calculation do? It will give you both the frequency as well as the amplitude without any approximations. And that's where Heisenberg comes in. In his 1925 paper, he provided precisely this breakthrough. He said, I'll apply quantum conditions and I'll be guided by correspondence principle. Because quantum conditions gives you the right frequency, but I want to calculate the intensities also. So I have already talked about quantum condition. I'll talk a bit about correspondence principle, which usually is about half a page in all quantum mechanics books, but it is much more important, as important as quantum mechanics, because it led to the development of quantum mechanics. So what is correspondence principle? Is any theory, new or old, any new theory should match with the established theory. What it meant was, if I am developing quantum mechanics, right, it should, in the limit of large energies, large systems, it should go to classical theory. And I have to make that correspondence all the time, right? So let's see, what does it mean? It provides a bridge from classical to quantum world, and it's not surprising. What it basically means, just a bit of math. Classical mechanics, the frequency is actually a derivative of energy with respect to the action I talked about, right? Quantum mechanically, it goes to dE by dN. However, quantum mechanical, there is no continuous change of energy, there is no continuous change of levels, so this derivative has to be replaced by a difference. So you see, this is the frequency, right, that we observe classically, and quantum mechanically, if you observe this should go to this, and everything sits well. Let me just show you through this through an example, and that example also then sets the stage for transitioning to what Heisenberg did. I'll illustrate it through particle in a box, and I've calculated this energy using quantum condition, which is proportional to n square. And if you calculate the frequency of light when it makes a transition from n to n minus 1, it comes out to be 2n plus 1 times all this, right? This is the quantum condition application. However, if I compare it with classical frequency, that is when n goes to infinity, you can ignore this one and it goes to whatever NH by 4 ml square, and this is precisely the classical frequency, 1 over the period, which I'll call the fundamental classical frequency or the first harmonic. If the level changes more than 1, there will be an alpha or that number out here. Note that this is also equal to 1 over h dE by dN in that limit. So this is the correspondence principle as far as the frequency is concerned, right? If I go further to calculate the other frequencies that the system can emit, this is the displacement of the particle in a box. It's a triangular kind of x versus t. And if you write a Fourier series, it comes out to be odd multiples of this basic frequency I just calculated. That means this contains not only the fundamental frequency or the first harmonic, but third harmonic, fifth harmonic, and so on. And this particle would be emitting all these frequencies. So this is all purely classical calculation. What does it mean as far as inference for quantum transitions is concerned? This is giving me the alpha omega n0, that is the fundamental frequency, is nothing but alpha times this derivative, right? This is a classical calculation, and quantum mechanically it corresponds to the difference between, or this should be n minus alpha, right? So existence of these fundamental and higher harmonics is related to the fundamental n plus minus 1 and plus minus 3 plus minus odd number. This is a transition, this is the correspondence principle. In old quantum theory, this was used to find the selection rules. The selection rule out here would be that particle in a box can make transition only through this difference of 1, 3, 5 and so on. People got all sorts of, Zeeman splitting selection rule could be gotten from here, polarization one could get there. So this played an important role. Notice what one is doing now is correspondence principle said that quantum all calculations should go to classical. We are working backwards. I know the classical answer, I am trying to guess what quantum mechanics does, alright? And this is precisely what Heisenberg would do. I can also just try to guess what the power related is. You see, once I write this frequency, for each frequency I have an amplitude. And I'm writing deliberately n minus tau, that is the transition, the jump through tau levels. This is the amplitude and I can apply it and get the answer. This answer again is not correct because I'm mixing ideas. I'm calculating amplitude through a Fourier analysis using some sort of an other things. So quantum mechanically it's not correct, except that I do not know how to calculate this quantum mechanically. Classically I could write a Fourier series, quantum mechanically I do not know. And this is precisely where Heisenberg makes a big quantum leap. Alright? He was suffering from hay fever and he was asked to go to this island, Heligoland, right? Which had no plants, no trees, so that he gets away from this hay fever. And that is where in June of year 1925, here on Helgoland, the 23-year-old Werner Heisenberg succeeded in the breakthrough in the formulation of quantum mechanics, the fundamental theory of the laws of nature in the atomic domain, which has profoundly influenced human thought far beyond. That's the plaque on Helgoland. Alright, so he was 23-year-old at that time. What did he do? Right? He wrote a paper which can be called, and some of the publications have called this, Heisenberg's magical paper. Why do we call it magical? Because he does things as if he is pulling things out of hat. And that's what I want to explain to you. Something like what you could also call for Ramanujan. Ramanujan did exactly the same thing. If you look at this formula of pi for him, 1 over pi equals some crazy series, right? So, in that sense, they're both magicians. They pulled something out of the hat. And I just want to focus on Heisenberg, who said in this paper that I'll stay as close to classical as possible, except when necessary. And that necessity was to abandon classical kinematic description. Dynamics will keep the same as classical. So, first thing he says is, it is not possible to associate an electron with a point in space. We don't see it, right? Discard hopes of observing position and period of an electron. And what it means is that the expansion, the Fourier expansion is meaningless. It cannot be done because I can't see it. If it is meaningless, what do? What I do is, it is still possible to ascribe to an electron because it emits radiation. There's frequencies and there's some amplitude, right? So therefore, I should develop my theory in terms of frequencies and the amplitudes, right? Why chose amplitude? Because it can be related to position when you go to large n numbers. So we will be working in terms of frequencies and amplitudes. Amplitudes are not actually displacement. They are related to the intensity of radiation. But they represent the position of an electron in the sense that when you go over to large n, they do represent displacement. So that correspondence comes in handy, right? So therefore, I'm going to write that the displacement, something that represents displacement, is going to be this amplitude times the frequency, and these are two quantum quantities. As n goes to infinity, displacement will become the real part of this. In that sense, I'm going to call this the displacement of the electron. But understanding that it is only in the n equals tending to infinity limit, in quantum regime, there are some amplitude related to intensity. And writing this in the complex form also makes development of quantum algebra quite straightforward, as we'll see. So in the n tending to infinity limit, the tauth harmonic, right? Remember I talked about the first harmonic, which is the transition from n to n minus 1. Tauth harmonic would be this amplitude plus its complex conjugate, right? This plus complex conjugate. Therefore, the first thing we find out is that this amplitudes have to be related. They have to be complex conjugate of each other if I switch the indices. That means if there's a emission, it comes down, there's a particular amplitude, while going up, it absorbs radiation, the amplitude has to be complex conjugate. And this is very important. All these, he discovers, follow quantum algebra, which is like the matrices. Summation is like sum of the matrices, right? So ZMN, if two quantum quantities have to be added to find Z, they will be added like matrix. The amplitudes and everything will be added like matrix. If I want to multiply, right, then the multiplication will be exactly like matrix multiplication. I want to point out, though, it looks very easy, that Heisenberg or any other physicists at that time were not taught matrices in their mathematics courses. They did not know about matrices. The beauty of Heisenberg was that he proposed this rule on the basis of an experimental observation. And here is the experimental observation. If I am talking about, before that, the quantum mechanical multiplication therefore is not commutative, xy is not equal to yx, and that has profound implications because uncertainty is based on that. So what he does is uses this frequency sum rule, which is given here, that if you take a frequency of jumping from n to n minus beta, it's sum of two frequencies to an intermediate level. That's what it is. So since all these quantities have to have the same frequency, frequencies are only those which are observable, so I cannot have an arbitrary frequency. So they have to be multiplied in such a way that the frequencies come out right. So if I am multiplying this something with frequency n minus alpha and n minus beta, the intermediate has to be like this. And then you get the same frequency on this side through this combination formula, right? And so this becomes the multiplication formula. Please keep in mind now, this is like as if I am adding probabilities of jumping from here to here, here to here, multiplying them and adding them up to get the total probability. Adding all the processes that go up make this jump. So this is like that, except that now I multiply amplitudes, not the probabilities. So that was, you can really anticipate that the interference terms. If I make the square of this, there will be cross terms. So what is quantum mechanical description then? Quantum mechanical description of an electron would require all these frequencies and amplitudes, right? And it has already been established that they are complex conjugates of each other. So you put this as a matrix, and since they multiply and add like matrices, so I put it like a matrix, and I need all of them in one shot because any manipulation would require all the elements. Consequently, the velocity would be the derivative of this, and it will be this. So one part is done, the kinematic part is done. What do I do next? Next I need the equation of motion, and as I said earlier, Heisenberg wanted to stay as close to as possible to classical ideas. So he does this, whatever the kinematic description has been changed, now the equation of motion has to be the same as classical equation of motion, but for each element of the matrix. So idea is to keep quantum mechanical formula as close to classical as possible. And next big thing is quantum condition. Remember what is the quantum condition? That P dot dl, now I can write in terms of velocity mv square dt for one period has to be nh. Replace this condition, first thing he says is replace it by a differential condition. Because integral condition means I'm assuming that constant is 0, which need not be. Let me write it in a differential form, integrate later, and then find that constant. So he replaces this, writes this whole thing using classical formula, and then transforms it into quantum formula using again the Heisenberg, the correspondence principle. Right? His ingenuity lies right here, how he writes this beautifully so that he can transform this. So what he does is, classically, this is the velocity, I have already written that, right? And then you square it here. By the way, I am taking little deviation, the calculation is exactly the same as Heisenberg's paper, except I am writing this in the form of these two indices, so that you see how I'll transform to quantum. So he multiplies this, writes these, you see this n minus alpha, n minus beta n, so that they cancel. Once I integrate, the sum equals 0 has to come here. So he writes it in this form, and then since these frequencies has to cancel when I integrate over t, so only n minus alpha and n minus alpha n, they remain. So I get mod x n n minus alpha square, frequency square, and dt gives you the time period, which is 2 pi by n, the fundamental frequency. One of the frequencies divided by this is alpha, and this. This is the form that he gets. And then one has to write the quantum condition in terms of this. This is where he uses correspondence principle. So I'm going a little slow over this. So d by dn of this is going to be 2 pi m, right? And times alpha d by dn, this. Now I have to interpret what this means, alpha d by dn, right? So I'll do that next. So quantum mechanically, the derivatives are, when I take the first derivative, I showed you earlier it is nothing but difference through n, 1. Alpha dy by dn, and I did this in terms of frequency, in general would mean that I take the top difference by alpha. So n dy by dn would mean difference by alpha. And that's applied now to write the quantum condition. 2 pi m alpha d by dn, this therefore means the difference of this quantity through alpha, n plus alpha to n, right? This is the quantum condition. This should be equal to h. So the quantum condition comes out to be this. And this is precisely what was later written by Max Born and Jordan as, the x dot p equals IH cross, or Dirac also as in terms of IH cross Poisson brackets. So this is his quantum condition. So just to sum up, this is a quantum theoretical description. Only changes are made in kinematic description of the electron. They are represented by matrices. These matrices satisfy the classical equation of motion, and this is the quantum condition. So I've developed this. I should be able to get the right answers through this. So now he applies it to a simple harmonic oscillator of angular frequency omega. Again, I'm going to take liberty of deviating slightly from Heisenberg's paper and use a correspondence principle, because otherwise that calculation becomes long. I'm keeping it as simple harmonic oscillator without any n-harmonic term. He did an n-harmonic oscillator so that he could get a recursive relationship. I'm going to say that in the n equals infinity limit, there is only one frequency omega, right, for the harmonic oscillator. Therefore, maximum difference between two levels can be plus minus 1. So classical fundamental frequency is omega. By correspondence principle, the first harmonic is omega n minus 1 is this, and therefore you put it here, x n plus minus 1 is going to be 0. For all other frequencies, this amplitude is going to be 0. Just pure correspondence argument. Once I have gotten this, so I have one frequency omega, and corresponding amplitude 0, non-zero for that frequency, rest is all 0. Put it in the quantum condition, you get this. Through this, you get the amplitude. And this constant is 0 because if I take the ground state to be n equals 0, there should be no amplitude. There is no radiation coming out of the ground state. And therefore, xn n minus 1 is determined purely through quantum arguments. Right? And once I do that, I can substitute this in the energy. Energy is nothing but it comes out to be diagonal, and therefore there is no time dependence in it. It's conserved. That's one great point about this calculation. You get conservation of energy right away, and you put in all those numbers, you get this as the energy. I'm still not done because I still want to check whether I'm all right or not. So En minus 1 comes out to be consistently with the frequency I started with. The whole calculation becomes consistent. Everything is fine. I can take those xn's. I can also calculate the intensity, right? So this is where I stop talking about Heisenberg's paper. I conclude Heisenberg's paper. Of course, this is a great achievement. See, all the calculation is purely quantum mechanical. There is no classical hodgepodge business. And this paper was soon followed by papers by Born and Jordan. Born, Heisenberg and Jordan, who developed the entire machinery of matrix mechanics, but the idea was taken from here. Independently, Schrodinger developed quantum mechanics the next year, 1926, and who also showed it to be equivalent to matrix mechanics. He wrote series of 6 papers, and he writes that when I was writing the first paper, I did not know what I was going to write in the second paper. Second one, I did not know what I am going to write in the third paper. In fact, people compare those 6 months to be Einstein's miracle year kind of time. And then independently, Dirac also worked to reformulate ideas of Heisenberg and write quantum conditions in terms of Poisson brackets. So that concludes our discussion about Heisenberg, how he started in 1925. So this began in 1925, the era of quantum mechanics, as a new conceptual formulation of its own, right, by this man, 23-year-old, on this island. And, the particular article which calls him the Columbus of quantum mechanics. So the era begins, and I stop by thanking you for your attention.
Swayam Prabha, Digital India, Educated India.